Good morning, everyone, and welcome to this lecture. This is lecture number 2, and we are dealing with nuclear physics. In the last lecture, we had seen the important factors about nuclear reactions, and we were dealing with whenever we are dealing with a nuclear reaction or collision, you must have a parent nucleus, then you have a particle which is incident on it that gives you a daughter nucleus and maybe some other particles and some energy. Now this energy which is released or absorbed in a nuclear reaction is known as the Q value of this nuclear reaction, and this Q value of this nuclear reaction can be written in various forms. It can be written in the form of mass of the reactants minus mass of the products into C square. It can be also written in the form of the kinetic energy. The difference in the kinetic energy is kinetic energy of the products minus the kinetic energy of the reactants. It can also be written in the form of binding energy of the product minus binding energy of the reactants. We have also seen how we can apply law of conservation of energy in any nuclear reaction. Three things we have to apply: law of conservation of A and Z, atomic number and mass number, law of conservation of momentum, and law of conservation of kinetic energy. We had seen some examples there, and I think we were dealing with this question when we ended the class, so we will start with this question. Binding energy per nucleon versus mass number curve for nuclei is shown in the figure WXYZ of 4 nuclei. Which process should release energy? I'll give you 2 minutes to solve it. So how are we supposed to do this? Remember, the process that would release energy has to be released. That means for this process, the Q value has to be how much? The Q value of the reaction has to be positive. The Q value of the reaction has to be positive. Then only the reaction will release energy. If Q value is negative, it is known as an endothermic reaction. It will need to absorb energy. So we have to find out for which of the equations we have exothermic reaction. Now, to find out this, Q value is the binding energy of products minus binding energy of the reactants. We have to find out the binding energy of all these particles. What is the binding energy of this? Binding energy per nucleon is 5, and there are 30 number of nucleons, so the binding energy of this is 150. The binding energy of this Y, it has 60 uh, nucleon, and that is multiplied by 8.5, so 60 into 8.5. I think how much would that be? I think that would be equal to somewhere around 51. Oh, sorry, 510. 6 into 8 is 480, and then you add 30, so 510. For x, it would be 8 multiplied by 90, so it would be 540. For w, it will be 120 multiplied by 7.5. How much is that? 120 into 7, 12 sevens are, I think it is 84, and you add 60, so this would be, I think, 900 if I'm not wrong. It should be 900. Let me check. .5 multiplied by 120, 900. Correct. Now I have to see for which reaction the Q value is positive. The binding energy of the product should be more. If you look at this one, 2Z is 300. It's less than 510. Not possible. W is equal to x plus z. If you add x plus z, it will be 690 and W is 900. This is also not possible, so this goes away. Let us look at the fourth equation. X plus z. No. X plus z. This equation, x plus z is 690 and W is 900. So obviously this is not possible. I got confused. Then we come to the fourth equation. X is 540 and y plus z is more than that. So this is not possible. 2 times y is 1000 something and W is 900. This is the only reaction in which Q value will come as positive. Remember, Q value is binding energy of products minus binding energy of reactants, and that must be coming as positive. It is only coming positive in the third case, and that is the reason of this answer. I'll give you 1 minute to note this down. Once you are done, please let me know. And if you have to send any message, you send it on the ID. I will name it at Ask Chat. You send message on that. Otherwise, your message come on my laptop and it's very difficult for me to do anything. So Ask Chat, I have created this. Whatever message you have to send in on that. Give you 2 minutes to note this down. Well, I'll move ahead again. I would ask you not to send the chat to everyone. It comes on my laptop and it becomes difficult for me. You send your message on the ID that I have created. Click it, put chat, and then put your message in that Ask Chat ID, not to everyone. Okay. Again, this is a question taken from one of the previous year IITs, and these are the questions that are going to come. So let us concentrate on these questions. A nucleus with mass number of 220 is initially at rest. It emits an alpha particle. I hope you understand what is an alpha particle. An alpha particle is a helium nucleus. The Q value for the reaction is 5.5. It is positive. The Q value is positive. I will give you in points just after this question. Again, what do you mean by a positive Q value and negative Q value? The Q value of this reaction is positive 5.5. I've already told you about the Q values. Calculate the kinetic energy of the alpha particle. And it's a very important message and point that you will get from this. This is actually known as an alpha emission. Alpha emission. This is radioactivity. Officially, we have not started it, but unstable nucleus, a nucleus which has got an atomic a mass number more than 220, here it is exactly 220, it emits an alpha particle to become more stable radioactivity. Anyways, this is the question, and let's see how you're going to do this. I'll give you a hint in solving this problem. This is how the reaction looks like. This is your X, the parent atom. Oh, sorry, I should not call it atom. Parent nucleus. It gives rise to a daughter nucleus Y, which has got a mass number of 216, plus you have the alpha particle, which is nothing but a helium nucleus. So I will write it like this: helium 4 2. Mass number is 4, atomic number is 2. The mass number is 4, which is given over here. It will have some kinetic energy. They have called that kinetic energy as K2. It will have some momentum. They have called the momentum as a P2. This parent, the daughter nucleus will also have some kinetic energy. Let us call it as K1. It will have some momentum. Let us call it as P1. Remember, the mother nucleus, the kinetic energy was zero, as well as the momentum was also zero. So this is the hint that I am going to give you. I'll give you 2 minutes to solve it. If not, I'll solve it after 2 minutes. Let me go ahead and solve this question for you. Now, it is given that in the question that the Q value of this reaction is, it's an exothermic reaction. It gives out energy. Q value is positive, plus 5.5 mega electron volt. So let us start from that point. Q value of the reaction is the kinetic energy of the products minus kinetic energy of the reactants, and as you can see, the kinetic energy of the reactants is zero. So kinetic energy of the products, that will be equal to 5.5 mega electron volt. Kinetic energy of the products, here I can write it as K1 plus K2, that will be equal to 5.5. I hope all of you understand this, that K1 plus K2 will be coming as 5.5. This is coming from the Q value, the definition of the Q value. Let me know, you can just raise your hands in the chat and I will understand that you have got this. K1 plus K2 will be equal to 5.5. Now remember that the initial momentum of the system was zero, and therefore the final momentum of the system would be zero, and that is the reason that if this alpha particle moves like this with a momentum p1, the daughter nucleus must move like this with a momentum p2. If I talk in terms of the magnitude of the two momentums, the magnitudes of the two momentum p1 shall be equal to p2. I hope you understand this. Now, we know that how you can write momentum. You can write momentum as 2 times mass into kinetic energy, 2 times m1 into k1 ka root, that will be equal to root over 2 times m2 into k2. Now, whenever this question comes, this will be coming with a nucleus of 220, because 216 is a perfect root, I think. M1. So, M1 into K1 shall be equal to M2 into K2. I hope you understand this. Yes or no? M1, the mass of the first one is 216 into K1. That would be equal to M2, which is 4 into K2. Sorry, 216 is not, 196 is the square of 16. I got confused. So in any case, the root is going to get cancelled from here. From here, you will understand K1, the relation between K1 and K2. I think 54 times K1 shall be equal to K2. This is the second relation. From here, you can find out the value of K1, which is the kinetic energy of the daughter nucleus, and K2, which is the kinetic energy of the alpha particles. And a very astounding result you will get the value of K2 as 5.4 mega electron volt. You will get the value of K2 as 5.4 mega electron volt. Now what you have to understand is the Q value of this reaction was 5.5, and almost the entire energy of this reaction is taken by the alpha particle. A very important result. In an alpha decay, this is known as an alpha decay. We are just going to see this. In an alpha decay, almost all energy is taken by the alpha particle. Now, if you know this fact, If you know this fact, actually there is no need to solve this question. The Q value is 5.5. The alpha particle cannot have energy more than that. The only option which is possible is 5.4. So you actually would not have to solve the question if you remember this fact. I hope you have understood this. I've applied here two things. Sorry, I've applied here three things. The first thing is law of conservation of mass, law of conservation of A and Z. I have written the equation. In this equation, A and Z would be equated. I do not know the value of Z. I know the value of A. I always get confused between A and Z. So this is 220 and this is 216. I hope everyone understands this. Yes or no? Please raise your hand so that I understand this. I'll give you 2 minutes to note this down. Let us go ahead and move on to the next thing, and let us again go back to nuclear reaction. There is a point that I have to tell you, and there was a question on you on the same point in your previous year JEE. We'll also see that question. The heading you can write is Q values. We are still in Q values, and we are going to see more on this. Now the reaction that we had seen, the nuclear reaction that we had seen was this A was your bombarding particle. I hope you remember this. This A was your bombarding particle or incident particle. This X is your parent nucleus. This Y is your daughter nucleus. I hope you remember what I am telling you. I am trying to tell you the nuclear reaction. We had seen this nuclear reaction, and I'll show you. Just trying to write this nuclear reaction again, and trying to make more points on this, because a point came last year. So B is your product particle. We call it the product particle. Plus you have Q, which is the Q value of this reaction. Now remember, if the value of Q comes out to be 0, if the value of Q comes out to be 0, window has closed, the value of Q comes out to be 0, that means the kinetic energy of the products shall be equal to the kinetic energy of the reactants. The kinetic energy of the products shall be equal to the kinetic energy of the reactants sorry. If the value of Q is coming as 0, this will imply that kinetic energy of the products will be equal to kinetic energy of the reactants. I have not seen many reactions happening like this. This reaction would be a perfectly elastic collision. This reaction would be a perfectly elastic collision. I have not seen nuclear reaction like that. Let us move on to the second case. If the value of Q is greater than 0, that means Q is positive, it's an exothermic reaction. It's an exothermic reaction. Energy is given out. Now, such reaction where energy is given out can happen on their own. They don't need any external energy to help them in doing this reaction. So even if the kinetic energy of the particle A is 0, this reaction can happen on its own. You don't need you don't need you don't need you don't need any kinetic energy. If this particle A just touches it like this, then only this reaction can happen. When does this reaction will not happen on its own? We need to input energy. That would be the third case. If the value of Q is less than 0, then this reaction becomes endothermic. That means energy is required. Or energy is absorbed in this particular reaction. Energy is required to carry on this reaction. Now, if energy is required to carry out this reaction, this energy has to be given to this energy has to be given. Now, how will this energy be given? This energy will be given in the form of kinetic energy of the bombarding particle. The minimum energy which is required to carry on this reaction is known as the threshold energy. And the value of that threshold energy can be found out in this way. It will be minus Q. Why minus Q? Because Q is negative, so minus of Q becomes positive. 1 plus m1 by m2, where m1 is the mass of the projectile. When I say projectile, in this case, it is the mass of the particle A. m2 is the mass of the target. In this case, it is the mass of the parent nucleus X. I can write E threshold as Q value की absolute value into mass of A divided by X plus 1. This is the way I remember it. And I'll give you 2 minutes to note this down. I hope we have understood this. Yes or no? No or yes? Anyone understands this? I'll give you 2 minutes to note this down. That takes us to this question. And this is the question that I was talking about. This is your question from JEE Advanced 2022 last year, paper 1, section 1, question 2, numerical type +3 and 0. The minimum kinetic energy needed by an alpha particle to cause the nuclear reaction this in a laboratory frame is N in mega electron volt. Assuming that nitrogen 16 is at rest in the laboratory frame, and some things are given. You have to find out the value of N. I'll give you 2 minutes to solve this. You will have to do precise calculations for this question, because it's all about calculations. It's all about calculation, my dear friend. Correct to 2 decimal places. That's what the paper says. Correct to 2 decimal places. So let me solve this one for your purpose. The You have to find out the minimum kinetic energy. That means you have to find out the threshold energy, and you already know the formula of the threshold energy. This will be equal to the value of Q value into 1 plus the rest nucleus is 16, so you have to find out the mass number of nitrogen, and you can take it as 16 divided by the mass number of I'm doing ulta. The bombarding particle is helium. A is helium, so the mass number is 14 divided by the mass number of the parent nucleus is 16. So I think this will come as the Q value multiplied by 5 by 4. So you just have to find out the Q value of this reaction and multiply it by 5 by 4. The Q value of this reaction will be mass of the product. So mass of the mass of the reactants, mass of nitrogen nucleus minus mass plus mass of helium nucleus, that is the reactants, minus mass of hydrogen plus mass of oxygen. And you will see here that the Q value is going to be coming out negative. Let me put the values of mass of nitrogen is 16.006 plus mass of helium is 4.003 minus mass of hydrogen is 1.008 plus mass of oxygen is 19.003, and I multiply this entire thing by 930. I multiply this entire thing by 930. I hope everyone is able to understand this. The Q value is going to come, the answer that I have is minus 1.88 mega electron volt. Once you get the value of Q value as negative, you need certain minimum energy, and that minimum energy will be given by, take the positive side, 1.88 multiplied by 5 by 4, and the answer rounded to two places of decimal is going to come as 2.33 mega electron volt. As you can see, this question is pretty simple, but it requires calculation. You'll have to add and subtract the atomic masses in AMUs, then you have to multiply it by 930, and then you have to again divide and multiply. If you're not sure about your calculation, or if you think that you can make a mistake here, there are no options given here. Even if you know this question, you can skip it in the first attempt, and when you get time, then you can come back and solve this question of this type. I hope you have understood this. I'll give you 2 minutes to note this down. Then we come to the next heading, and the next heading is radioactivity. What do we understand by radioactivity? We have seen that as the mass number of when the mass number is very less, then also the nucleus is very unstable, but when the mass number is high, then also the nucleus is unstable. If you have an unstable nuclei or nucleus, it will always try to get to a state of a stable nucleus. So what will happen? It will decay or disintegrate spontaneously on its own. Q value will be positive. It will disintegrate spontaneously, and it will get itself converted into some stable nucleus. In this phenomena, some types of particles or rays would be emitted. Either it will be alpha or beta or gamma. We will see what is alpha or beta or gamma. So by emitting alpha rays or beta rays or gamma rays, it is going to convert itself into a more stable nuclei. This phenomena is known as radioactivity or radioactive decay. Now, we are all aware that an alpha particle is nothing but a helium nucleus. Double check, double thing. Alpha particle is a doubly charged helium nucleus. That means the electrons have been removed. It consists of 2 protons, 2 neutrons. Mass of the alpha particle is approximately equal to 4 times the mass of the proton. Charge of an alpha particle, since we are talking about alpha, beta and gamma, this is what an alpha particle is all about. Since I have no space left, I'll give you 2 minutes to note this down. The next page, we will see what is a beta and what is a gamma particle. Then we come to the next particle. Just for your reference, I have kept alpha particle here, beta particle. Two types of beta particle here. The first type is known as beta negative, which is negatively charged, and therefore it is our old friend electron. The mass of the electron is Me and the charge of the electron is minus E. The second one is something which is known as a positron. I don't know whether you have heard this word. This positron has the same particle, same mass as the electron, but a charge which is opposite to that of an electron. Such particles are known as antiparticles. So positron is an antiparticle of an electron. What is an antiparticle? A particle is called an antiparticle, and these days we are searching for antimatter also. That is similar to antiparticle. If a particle is called antiparticle of other, if on collision they both annihilate. When I say annihilate, they finish each other. Dum. And what is left is pure energy. Two particles collide, bum. Everything finishes. The only thing that is left is energy. Those particles are known as antiparticles. Electron and positron are antiparticles. The other antiparticle that we will come across will be neutrino and antineutrino. We'll come to that. Neutrino and antineutrino are also antiparticles. When they collide, dumb, what is left is pure energy. Gamma rays. I told you, gamma radiation. Gamma are the most dangerous radiation. Gamma radiations are photons of energy which are emitted, and they have rest mass as 0. You must remember this gamma rays, photons, energy, photons, electromagnetic radiation is very harmful, very high energy. I'll give you 2 minutes to note this down. Then again, here is one more explanation. I've seen such questions in your JEE exam, and that is why I'm doing this. Here, what we have is an unstable, or now we will call it radioactive nucleus. Unstable or radioactive nucleus. Since it is unstable, what is going to happen? It is going to spontaneously disintegrate or decay, and it might emit jing, jing, alpha, beta, or gamma. The radiations will deflect towards the negative plate or alpha helium nucleus, which deflect towards the positive plate are beta particles, and these are basically electrons. We are not talking about beta positive. I'll tell you when beta positive happen. So these are stream of electrons, then therefore they are attracted towards the positive plate. They are known as beta rays. Radiations which go undeflected are gamma, gamma, gamma. These are EM waves of photons. Remember the next 2 points. No radioactive substance simultaneously emits alpha and beta. At the same time, it cannot emit alpha and beta. It can only emit one, either alpha or beta. After emitting alpha and beta, it can emit anything else. Also, gamma rays are emitted after the emission of alpha or beta particles. I've already told you, whenever we talk about these gamma radiations, whenever a unstable nucleus disintegrate. Sometimes it gives rise to a nucleus which is in an excited state. So this nucleus in an excited state will come back to its ground state by emitting some radiations. Those radiations are known as gamma radiations. 2 minutes to note this down. Point. These beta particles which are emitted, these beta particles are nothing but stream of electrons. They are not the electrons from the orbit. They are still, if there are any electrons in the orbit, they are still revolving. Those electrons are not emitted. These beta particles come from inside the nucleus. How these beta particles are produced? We will see that something is going to disintegrate here. A neutron will disintegrate and it will give rise to something else. We will see that in the next pages. I'll give you 2 minutes to note this down. Well, then these are some of the important points about radioactivity. Some question may come from here. And now also asking questions based on information. So radioactivity was discovered by Henry Becquerel. We will see how we have honored him. In the year 1896, after the discovery of radioactive uranium, Madame Curie, the only, 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 the only person in the entire universe who got Nobel in two different fields. Two Nobels in two different fields. One in physics, the other one in chemistry. Madame Marie Curie. They discovered she and her husband discovered radium. The radioactivity of a sample cannot be controlled by any physical methods or changes. All elements with atomic number greater than 82 are naturally radioactive. The conversion of lighter elements into radioactive elements. This is how you produce radioactive elements. You bombard lighter with the smaller ones, lighter ones which are readily present, you bombard them and you produce radioactive materials, and then you do all these funny things. Radioactivity is a nuclear event, not an atomic event. Just note down these points. Then we come to what we call as the first type of decay, which a radioactive nucleus can undergo, and that is known as an alpha decay. We have seen some part of this alpha decay previously. Now we will do it in much detail. What happens in an alpha decay? If you remember this curve, this is a curve between binding energy per nucleon and the number of nucleons, and we had said that any nucleus, when the mass number increases, it becomes unstable because the binding energy per nucleon goes below 7 and 7.5. In that case, when the number goes more than 220 or 210, it becomes unstable. When it becomes unstable, it can emit an alpha particle. By emitting an alpha particle, the nucleus becomes more stable because the binding energy per nucleon is decreased. So it tries to move in this stability range. By emitting alpha particles, it spontaneously decays, giving rise. This is what your parent nucleus is. This is your parent. This green one is your daughter. And this blue one is your helium nucleus, that is known as an alpha particle. Q value is the energy released in this decay process. And as you can see, this is a spontaneous decay, so the Q value will always be positive. How do you find out the Q value of this? You can subtract. This is nothing but equal to summation of mass of the reactants minus summation of mass of the products. I hope you understand this. Now remember, whenever we are taking its masses, mass of reactants, you have to take the mass of the nucleus, not the mass of the atom. You have to take the mass of the nucleus, but sometimes what is given to you in the question is the mass of the atom. Now the question that we did in from the previous year JEE, that was the mass of the nucleus, I guess. Sometimes the mass of the atom is given. Now here they have taken the mass of the atom. Now when you have mass of the atom, it also includes the mass of the electrons inside it, and therefore you have to subtract the mass of the electrons from the mass of the atom to get the mass of the nucleus. Here the daughter element, the daughter nucleus, will have mass number 4 less than the original one, and atomic number 2 less than the original parent nucleus. The Q value will be mass of the nucleus of the reactants minus mass of the nucleus of the products multiplied by 931 or Z square. Now here the mass of the here the number of electrons on the left hand side and number of electrons on the right hand side are equal. So what will happen is that these two values, 2 times mass of electron and 2 times mass of electron, will get cancelled, and the final Q value that you get will be equal to mass of X, whether it is the mass of atom of X or whether it is the mass of nucleus of X. Mass of X minus mass of Y minus mass of helium into C square, or you can write it as mass of X minus mass of Y minus mass of helium multiplied by 931.5, and the answer would be in mega electron volts. Do we understand this? Here the mass of the electrons is going to cancel from both sides. Remember, in some cases mass of the atom is given, in some cases mass of the nucleus is given. If mass of the nucleus is given, there is no problem at all. The mass of atom is given, you'll have to subtract the mass of the electrons. Here mass of the electrons will get cancelled from both sides. So the formula remains same, whether you use the mass of the atom or whether you use the mass of the nucleus. I hope you understand this. I'll give you 2 minutes to note this down. Then we can move on to this part where we find out the kinetic energy of the following products. We have already done a question. The kinetic energy of the alpha particle will be A minus 4 divided by A into Q. This is the short form. The kinetic energy of the Y, the daughter nucleus, will be A minus 4 upon A, where A is the mass number of the parent nucleus. Remember, almost all of the energy is taken by the alpha particle. We have done this question. This is just a proof of this. Now, if we assume that all the alpha particles are moving with the same kinetic energy, if you put a magnetic field R is equal to mv by qb, you can find out the radius of these alpha particles when they are moving in a magnetic field. Now this question is out of the scope of JEE Main. This is the question more in the domain of a difficult JEE paper, where after these particles are emitted, they would ask you what would be the radius of the circle in which they will move. I'm giving you everything so that if a question comes, you are not found wanting. 2 minutes, you have to note this down. Once you note it down, let me know. Remember, in this, you don't have to note down everything. I forgot to tell you. You just have to note down these final results: kinetic energy of alpha particle, kinetic energy of the daughter nucleus. Just have to note down these results. You don't have to write the entire thing. It's not required. And the formulae for radius. That is what you need to do. You don't have to write out everything. You will not have even time to study it again, read it again. Again, in this particular thing, you don't have to write anything. This is just a curve of nuclear stability. You just have to draw the curve. This stability of the nucleus, apart from the binding energy per nucleon, we can also understand it in terms of the N by Z ratio. N is the number of neutrons, Z is the number of protons. You can understand the nuclear stability by the number of neutrons and number of protons. If the number of neutrons and number of protons is same, so you have a line at an angle of 45 degrees, we can call these light nucleus as stable. Now, if the number of neutrons increase till the time there where this N by Z ratio becomes your 1.6, N by Z ratio becomes 1.6. In this blue zone between these two lines, this blue zone between these two lines is the zone which we call as the zone of stable nucleus. Between a straight line N by Z is equal to 1 and between this curve where N by Z is equal to 1.6, we have the zone where the nucleus is stable. If a nucleus lies in the yellow zone, it is unstable. It will emit a beta negative particle and become stable. If it is on this side, on the right hand side of this stability zone, it will emit a beta plus particle and it will come into the stable zone. So no matter what happens, they will try to get to that stable zone. You don't have to write anything else. You just have to draw this diagram. N is equal to 1, N is equal to N by Z is equal to 1, N by Z is equal to 1.6. In between this, you have stable zone. On the left of this zone, if a nucleus is, it will emit beta negative. On the right of it, if it is, it will emit beta plus and get into that stable zone. I'll give you a minute to note this down. So this beta decay comes from this N by Z ratio. You see the zone of stability. If the N by Z ratio of your nucleus is more than the stability, it will emit a beta negative particle and it will get to the stability zone. This is how the equation looks like. Here a neutron breaks up. Neutron breaks up into a proton. It gives an electron and it gives anti-neutrino. This is your anti-neutrino. This is your anti-neutrino. This is your anti-neutrino. The entire kinetic energy is taken up by the beta particle and the anti-neutrino. So Q value of this reaction, apart from the mass defect, you can also find it from the mass defect. You can find it from kinetic energy of the beta particle and kinetic energy or the energy of the antineutrino. Do we understand this? Everyone, please send me a thumbs up so that I understand that you've understood this. I'll give you 2 minutes to note this down. Here, just make a small thing here that might confuse you because I have not seen question of this type. The You can remove this part and you can just take, because antineutrino is energy. The Q value of this is approximately equal to the kinetic energy of the beta particle. Almost the entire energy is taken away by the beta particle. A very small amount of energy is going with the Y particle, the Y parent atom, the Y parent, the daughter nucleus, and a very small amount of energy goes to this antineutrino. So if someone asks you to find out the kinetic energy of the beta particle, it will be approximately equal to the kinetic energy or maximum possible kinetic energy of the electron which is emitted. But I've not seen question where they give you the mass of the antineutrino. They are not going to ask you the energy of antineutrino. Let me know once you are done. Then we come to this part where we see this beta negative decay. Let me write it in bigger thing. What happens in a beta negative decay? You have a parent nucleus Az. It gives you a daughter nucleus. The mass number remains same, but the atomic number increases by 1, and you have an electron or a beta particle emitted. Sometimes instead of writing it as like this, you can also write it like this. Doesn't matter, is the one and the same thing. Plus you have an antineutrino which is given up. Now what is happening, how this reaction is happening inside the nucleus? A neutron is getting converted into a proton. Proton has a mass number of 1 and an atomic number of 1, plus it gives out an electron. Neutron has a mass number of 1, charge or atomic number as 0, plus an antineutrino. So what you can see here is this reaction is taking place inside the nucleus. I hope you understand this. This reaction is taking place inside the nucleus. This reaction is taking place inside the nucleus, and therefore the beta particle and the antineutrino that is emitted from inside the nucleus. Now if you want to find out the Q value for this, here again the mass of the atom of X, Y and mass of the electron is given. You again find out the mass of the reactants and subtract the mass of the products from here. When you do that, you will get the answer as mx minus my. Here also the number of electrons will get cancelled. So the Q value will be equal to mass of X minus mass of Y into C square, or if it is in mega electron volt, if it is in AMU, you can multiply it by 931.5. You will get the answer in mega electron volt. Here also the electron is getting cancelled from both sides. There is one reaction in which it is not going to happen, and that is why I am telling you this. I'll give you 2 minutes to note this down. And you come to this one, which is B plus emission. We call such type of nucleus as B type. They lie on the right hand side of the curve. That means the N by Z ratio for this B type is less than the N by Z for the stable zone. So what happens is that they emit a beta particle, they lie on this side, they emit the beta particle, which is a positron, and they come into the stability zone. This is the equation that happens inside the nucleus. Inside the nucleus, what happens is a proton, as you can see P, a proton gets converted into neutron. It gives out a positron and neutrino. If I represent this equation in the form of parent and daughter, it looks in this form. A xz will become y a z minus 1, atomic number decreases by 1. It gives out a beta positive particle and neutrino. Now if I find the Q value of this, if I use the mass of the atoms, you can see in the Q value 2 electrons, there is an imbalance of electrons. I should not say imbalance of electrons, the charges are positive, the charges are balanced, but because of electron being a positron being given out, not an electron, in the final equation you see mx minus my minus 2 times me. So Q value will be mx, mass of atom of x minus my minus 2 times me multiplied by 931.5 mega electron volts. Remember here I am considering mx and my as the mass of the atom. If the mass of the nucleus is given, you don't have to take the mass of the electron, because mass of the nucleus is the mass that we have to consider. Here the mass of the atom is given, and therefore this minus 2 me has come. I'll give you 2 minutes to note this down. And this is a simple question that you have to solve it. You have to find out the Q value in the following decays. Remember what is given here is the atomic masses, mass of the atom. Atomic masses are given. The atomic mass of electron is not given, so I will just give it. The atomic mass of an atom is 0.511 U, because you might be requiring this. And so here we are. There are two reactions given, and I hope you understand. The first one is a beta negative decay. The second one is a beta positive decay. Rest of the things are given to you. I'll give you 2 minutes to give me the answer for this one. It only requires multiplication and division. So how are we supposed to find this? Let us first solve the option A. The Q value for this reaction will be equal to mass of oxygen atom minus mass of fluorine atom multiplied by 931.5 or 930 or whatever you take it. So this will be nothing but equal to, remember this is a beta negative decay. The Q value will be equal to mass of oxygen 19.003576 minus mass of fluorine 18.998403. You have to multiply it by 931.5. The answer that I have is 4.816 mega electron volt. You just have to multiply, subtract, and divide. Multiply, add, subtract, nothing else. In the second case, I just wanted you to understand the formula. The Q value will be given by mass of aluminum atom minus mass of Mg atom minus 2 times the mass of an electron multiplied by 931.5 because this is a beta positive decay. I will just put the values and tell you the answer. The mass of aluminium is 24.990432 minus the mass of Mg atom is 24.985839 minus 2 into 0.511. Masses are like this. If this question comes in an examination hall, they might not give you so precise value, they might just give you approximate values. Multiplied by 931.5, the Q value for this reaction is going to come as 3.254. So this is how it has to be done. Everyone has understood this? Yes or no? I think I did a mistake here. This electron, this value is not 0.5111 U. This is not 0.511 U. I think I've done a mistake here. I don't. This is in terms of mega electron volts. It is 0.511. It is not 0.511 U. For an electron, this value is 0.511 mega electron volt when you convert it into energy. So I should not use this value here. I should use the mass of an electron, and mass of the electron can be written like this: 0.511 divided by c square. Basically, uh, I will just write it like this. This has to be multiplied by 931.5 and subtracted by 2 into 0.511. That would be a better way of writing this. I hope you have understood this. I made a mistake here. The mass of the electron was not given. I just wrote it. It was given the energy equivalent to 1 mu. The mass of one electron, that was 0.511 mega electron volt. This was beta minus capture and beta plus capture. Beta minus 1 emission and beta plus emission. I'll give you a minute to note this down. Let us go ahead and see the last type of, not the last, the third type of decay, which is known as a gamma decay. Now, whenever this radioactive nucleus, let us take the example of this radioactive decay, and this is the example that you will find in almost all the places. When we take this radioactive decay of cobalt, CO, what happens is it gives you nickel nucleus that you can see here. But this nickel nucleus, you can see a star here. This nickel nucleus is actually in an excited state. We know about the excited states of electrons in the energy orbits. Similar to excited states of electron, the nucleus is also sometimes, there are energy levels for nucleus as well. So when an unstable nucleus is emitting some alpha or beta negative particle, it may give rise, usually it will always give rise to a daughter nucleus which is in a higher energy state. You don't have to write everything. You just have to write this line that I'm underlining. Whenever a alpha or a beta emission is taking place in an unstable nuclei, the stable nuclei that you might get may be in a higher excited state. It will come down to its ground state and it will emit some radiations. Those radiations are known as gamma rays. So this excited nucleus gives you this gamma photon, and that is how gamma radiations are given. Therefore, it is said that gamma radiations can only be given after an alpha or a beta decay. As you can see here, this is the original parent nucleus. It gives rise to a daughter nucleus which is in an excited state. Therefore, it is going to emit gamma radiations. If it is in the first excited state, it will come to the ground state. If it is in second excited state, it will emit one gamma, come to the first excited state, then it may emit one more gamma and it may come to the ground state. That is how this gamma radiations are emitted. These are very high energy radiations and they are very harmful. I'll give you 2 minutes. You don't have to write everything. Just have to write the part that is highlighted. Then we come to the comparison alpha, beta and gamma. We have seen those things. This is just a comparison. What is an alpha particle? It is a helium nucleus. What is a beta particle? It is fast moving electron. What is a gamma particle? Well, my dear friends, it's a photon. Charge 2e, charge 2e minus e, it has got no charge. Mass in terms of protons, 4 times the mass of proton. This is equal to the mass of an electron. This is massless because it is nothing but a photon. Since it is a photon, it will move by the speed of light. This is an electron. It can have even 99% of the speed of light depending on the nucleus. The speed of this alpha particles is very small. These are the range of kinetic energies. You may remember them, you may not remember them. That is not of much importance. What you got to remember, the next point is the penetration power. Alpha particle can be stopped by a piece of paper. Gamma particle is 100 times that of alpha particle, and this gamma rays, they are very dangerous. I'll give you 2 minutes to note this down. Then we can move on to the other factors, the ionizing power. You just have to remember them. This is 10,000. It can ionize more because it consists of positively charged particles. Effect of electric or magnetic field, deflected, no effect. It consists of photons. Energy spectrum for alpha particles is line spectrum, discrete. This is continuous. This is line and discrete. You must remember this. These are photons, so they can produce all types of effects that electromagnetic radiations can produce. Now, equation of decay. This is the equation of decay. If there are n number of decays, this is the number of alpha particles that will be released. If there are n number of beta decays, this will be the number of beta particles that will be released. The question on this has come many times in the exam. I'll give you 2 minutes to note this down. Then there is this type of process. So very rare process. It's only found in a few nucleus. In this process, what will happen is that nucleus, as you can see, this nucleus is going to capture an electron from the K shell. Therefore, it is known as K capture. It will capture an electron from the K shell, a proton in the nucleus will combine with this electron from the K shell. They will neutralize each other, so they will give rise to a neutron and a neutrino. And this type of capture is known as K capture. If you write its equation in terms of atom, inside the atom, proton is going to capture one of the electrons, and the atomic number will decrease by 1. It will give you neutrino. Some energy would be released, so Q values, and you will have characteristic X-rays coming. Why will characteristic X-ray come? Because an electron which is vacant, inner shell is vacant, so you will have K series of X-rays being emitted here. Do we understand this? Please raise your raise your hand so that I can understand that you've understood this. If you write this in terms of nucleus, so nucleus has to take an electron from outside, and this is how the equation looks like. The third one is the Q value for this reaction. I hope everyone is able to understand this. Please raise your hands. You all understand this? The Q value is given by this. All nucleus from 84 to 112 will show radioactivity from 1 to 83. They are almost stable, only few exceptions. Whenever a neutron is produced, a very important result that you have to remember, wherever a neutron is produced, a neutrino is also produced. You can see here in this equation, a neutron is produced. There will also be a production of neutrino. Many times students ask me, sir, how do we find out where a neutrino is produced and where an antineutrino is produced? It confuses them a lot. This is what I tell them. Whenever a neutron is produced, a neutrino is also produced. Whenever a neutron is converted into a proton, an antineutrino is produced. And therefore, we have antineutrino produced in beta minus GK. Do we understand this? I'll give you 2 minutes to note this down. Very important results. Coming to the properties of antineutrino and neutrino, both are photons. Rest mass is 0. They move with the speed of light. Energy is mc square. Chargeless, spin quantum number plus or minus 2. Where do we get neutrino? Wherever a neutron is produced, beta plus decay or K capture, we get neutrino. Where a neutron is converted into a proton, you have antineutrino. We see this in the beta negative decay. I'll give you 2 minutes to note this down. Then we have this question: thorium 228 90 transforms to bismuth 212 83. Find the number of alpha and beta particles. These type of questions are in fashion these days. You might find them in the exam. So how are we supposed to do this? I have thorium 228 90 getting converted into bismuth 212 and 83. Now already given you the formula to find out the number of alpha particles. What you have to do, you have to just subtract a, the original mass number, minus a dash divided by 4. So it will be 228 minus 212 divided by 4, and I think you will end up with 4 alpha particles, my dear friends. three options have 4 alpha particles, so I have to also find the number of beta particles. The number of beta particles will be equal to number of alpha minus the original atomic number. Sorry, 2 times the number of alpha minus the number of the original atomic number plus the new atomic number z dash 2 into 4 minus 90 plus 83, and I think you will end up with 1. So the correct answer for this is 4 alpha particles and 1 beta particle. 4 alpha particle will reduce the atomic number by 8, then you have to increase it by 1. So 90 minus 8, 82 plus 1. You can do it in that way also. I don't know from where did you get 7. I hope you have understood this. This is the question, and I'll give you 2 minutes to solve this question. It's a simple and a straightforward one. A nucleus of mass number A originally at rest, and these are the type of questions that are going to come. And I just saw question the last year JEE Main paper coming on the similar line. The same question that we have done. The question that we are doing in the class, the same question are going to appear in your exam. 99.99%. Maybe the values are here and there. Sometimes the value will also be same. A nucleus of mass number A originally at rest emits an alpha particle with a speed v. The daughter nuclei, smaller, daughter nuclei recoils with how much of speed? You have 2 minutes to show me your talents. Option C is the correct option, my dear friends. This is the diagram. I have shown you this diagram before also. The momentum must be same. So momentum of this one, magnitude wise, m dash v dash should be equal to momentum of this mv. The mass of this is a minus 4 into v dash shall be equal to 4v. So v dash will be equal to 4v upon a minus 4, my dear friends. This is the answer that we were looking at. I hope all of you have understood this. Yes or no? No, yes. This is the question that appeared in 2022 JEE. A nucleus with mass number 184 initially at rest. Normally it will be at rest. Emits an alpha particle. The Q value of the reaction is 5.5. Calculate the kinetic energy of the alpha particle. And if you might recollect, we done exactly the same question. And I told you that this question can come. This came last year. I did not see it. Might have missed so many papers. I missed 1 or 2 questions here and there. Yes, my dear friends. Any hope of an answer? Shall I hope or shall I give up hope? Shall I hope or shall I give up? Option 4, you don't need to even calculate it. Most of the kinetic energy is taken by this. See? 1 second, you can give the answer. If, my dear friends, you can recollect what we have discussed in the class. I don't have that much faith in your ability to recollect, but then I have given you everything that can possibly come in the exam. If you will be able to recollect, you are going to reap lots of benefits. This one consists of things that we have done in the past as well. A particle of mass 4m disintegrates into 2 particles of m and 3m with non-zero velocities. The ratio of de Broglie wavelength, So this consists of disintegration also. This is exactly not a question of radioactivity, but I can relate it to this. What is the answer for this one, my dear friends? Any hope? Or shall I give it up? Yes, my dear friends. Any hope? Or shall I give up? You've done this question also before, I think. Similar question. It disintegrates. It was at rest. Obviously, we have forgotten. It was at rest. It disintegrates. Two particles. Obviously, they cannot go like this. I've gone mad. One particle goes here like this. The other particle goes here like this. They would have the same momentum, my dear friends. Momentum is same. The de Broglie wavelength lambda, and I guess that since it is 2 days old, you would have forgotten what was de Broglie wavelength. De Broglie wavelength lambda was h by p. The momentum of these two bodies are same, and therefore the answer is 1:1. I will not say much because I think you have forgotten it as expected. The only thing you have to forget is to forget things, but the only thing that you don't forget is the habit of forgetting things, and that habit is going to give you some very harsh results. Anyways, this is the next one. From the given data, the amount of energy required to break the nucleus of aluminium is 1 mu corresponds to x joules. So the answer has to be in joules. Find out the value of x. So basically what you got to do here is you have to find out the binding energy of this nucleus. To find out the binding energy of this nucleus, but you have to find out the mass defect. And what is the mass defect? So this is z times the mass of proton plus z minus a times the mass of the neutron. So I will find out the mass defect, my dear friends. Z is 13. So 13 multiplied by 1.00726. As you can see, this requires calculation. I know that you would find some trouble in that. I can't help you with this. Plus A minus Z is 14. 14 multiplied by mass of the neutron is 1.00866. That will be the mass defect. If you calculate this, the answer that I have is 0.02716 atomic mass unit. 0.02716 atomic mass unit. Now, it is given as x, and 1 AMU corresponds to x joules of energy. So how much energy will this correspond to? It will correspond to 10 raised to power minus 3 you have to put. So 27.16 x into 10 raised to the power of minus 3. Not x. That will be equal to, if I write, this is AMU, so x corresponds to this. So this will be 27.16 into 10 raised to the power minus 3 joules. 1 AMU corresponds to x joules. X multiplied by this, the answer would be 27.16. Do we understand how this is done? Oh, I have not subtracted the mass of aluminium. I did a mistake. Minus mass of aluminium. Mass of aluminium is given as 27.1886. So you have to subtract that mass also. So I convert I find out the mass defect. The mass defect will be coming in terms of mu, and from mu, 1 mu is given as x joules. So from there you can find out the value of x, 27.16. Do we understand how we have done this? Yes or no? Well, that brings us to an end of today's class. We are done with one portion of nuclear physics. We have started with radioactivity. We have seen what happens in radioactivity. A radioactive nucleus will spontaneously disintegrate, emitting beta minus or beta plus. Beta plus is rare, beta minus, and get to that stability zone by emitting beta minus, beta plus, gamma, or gamma can only be emitted by alpha and beta. After alpha and beta, now we will see. We have seen how it disintegrates. Now we will see what will be the number of particles that remain after a particular time. We will see its rate at which it is going to disintegrate. That we will do in the next class, when we will be winding off your nuclear physics. In the next class, you already have the sheets. If you just do these questions, they are good enough, because some of these questions would end up in your paper. As you saw, this question we had already done. We had done in terms of 220. No, not this one. This one, when we did this question previous year, it was 220. They just changed the value from 220 to 184, and they give you the answer. If you just pay attention in the class, it is good enough to you to crack any exam. For additional practice, you already have the sheets. Take care, and may God bless all of you. Bye bye.